Okay, as the first step in our detailed study of magnetically induced electromotive force, we consider a conductor moving in a magnetic field of length L in a uniform magnetic field perpendicular to the plane of the figure directed into the page. So this is of length L. There's a magnetic field going in this direction all the way across this plane. We give the conductor a constant velocity v to the right. A charged particle q in the conductor then experiences a force F equal to qv cross b. So there's a vector in this direction, and it's a force vector, and it comes about from qv cross b, because if you cross this v component with b, the magnetic vector, then you're going to be going in this direction, and you can see by going in that direction then the force is going there. Or another way you can do it is you can place your thumb in the direction of the velocity of the charged particle. So your thumb's going to, then your fingers point into the direction of the magnetic field vector, and then your palm will always be in the direction of the force. That's another way of working it out. So Q here being positive, the direction of this force is upward along the conductor from B towards A. Under the action of this force, the free charges in the conductor move, creating an axis of positive charge at end A and of negative charge at end B. The charge build-up, in turn, creates an electric field E in the direction from A to B. The accumulation of charge at the ends of the conductor continues until the E field, the electric field, is large enough for the downward electric field force, QE, to cancel exactly the upward magnetic force, QVB. So once these are equal, in this condition, the charges are in equilibrium with point A at a higher potential than point B. So we can set these two equal, so which I've done here. You can then rearrange this, because obviously the charges are going to cancel now, and you're left with E equals VB. And of course the potential difference then, if we've got a length L, remember that what we're talking about here is force per unit charge. Now force times distance is energy, joules, and joules per unit charge is volts. So we can say that the voltage from A to B is the same as VBL, or EL equals VBL. Now suppose the moving conductor slides along a stationary U-shaped conductor, as in this figure here. So no magnetic force acts on the charges in the stationary conductor, but it lies in the electrostatic field caused by the charge accumulations at A and B. So this part here is not moving with respect to the magnetic field, although this bar is moving. But what is happening here is this bar, because it's touching this bar, which is having these charges pushed up, if you like, having these positive charges moved from B to A due to the velocity of it moving, it means that is now within the electrostatic field of these moving charges. So under the action of the field, a current is established in the counterclockwise sense around this complete circuit. The moving conductor has become a source of electromotive force. Charge moves within it from lower to higher potential, and in the remainder of the circuit, charge moves from higher to lower potential. We call this a motional electromotive force, denoted by capital E. We can write E equals VBL. Okay, so now instead of writing the voltage, this here we can write as VBL. Okay, it's the electromotive force. And this is very much like a battery now. With this moving, we're pushing positive charges up in this direction, and when there's this imbalance of positive charge, then obviously they're going to move in this outer circuit here. So this is like the terminals of a battery, if you like, there and there, and then the circuit starts to move, and then when it comes back here, then obviously those charges are being pushed up by this movement again. So that's like the chemical reaction in a battery. Now if the resistance of the sliding bar is negligible, then the electromotive force E is also equal to the potential difference, VAB. For a real conductor with finite resistance R, there is potential drop IR. So this conductor in reality has got some resistance to it, so we call that little r, and that's going to cause a voltage drop. So some voltage is going to drop across this resistance of the bar. We write VAB equals electromotive force minus the drop IR. Note that this equation is exactly the same form of relationship that we use for the EMF terminal potential difference and current in a battery, although the origins of the two EMFs are completely different. If the velocity v of the conductor is not perpendicular to the magnetic field B, but makes an angle θ with it, then we replace v by v sine theta, and the induced EMF is this, v sine theta BL, so it's not just v BL anymore. More generally, we can define the electromotive force EMF as the line integral of the associated non-electrostatic force divided by the charge Q, to put it on a force per unit charge basis. This corresponds directly to our definition of potential difference as the line integral of the electric field E, the electrostatic force per unit charge. In the present situation, the non-electrostatic force per unit charge is V cross B, and we define the EMF as E, the integral of V cross B dot dl. So what we're saying there is, if you look at this equation, the force equals QV cross B, and what we're going to do is try and put it in the form of a potential difference. Well, we know that the force per unit charge in electric fields, for example, force per unit charge is the electric field. Well, we can do something similar here and you know that force times distance per unit charge is voltage. So all we want to do here is take this equation, divide it by a charge and multiply it by a length, and you've got a voltage. What we're saying is, if we divide through by the unit charge, we end up with V cross B, which is there, times that by the length, in other words the component of this vector along the length here, so along this length here, is going to be the equivalent of the EMF. So if we calculate the integral of V cross B dot dl between A and B, we have the equivalent potential difference between A and B. In this figure, the velocity vector V and the magnetic field vector B are perpendicular. Both are constant over the length of the bar, and their vector product is parallel to dl. Thus, in this case, equation 3 here reduces to VBL.